Hi, so I'm continuing on with atomic spectroscopy in the kind of second half of lecture 3 because it got a little long. Again, I'm speeding through this material relatively quickly. Hopefully it'll be familiar to most of you. And in this section, we're going to be specifically focusing on absorption and emission, as well as the really very starting point for spectrometry. Okay, so let's start with light absorption. The most important thing to realize about the absorption of light by any sample is that the color you see with your eye, if you're fortunate to be able to see the color, is actually not the color specifically that's being absorbed. And that's a really kind of counterintuitive but important point. I'm not going to go into it too much because it's more about perception of color, and spectrometers get around that. We don't use our eyes, luckily, when we do spectroscopy. We use detectors, but nevertheless, you should understand it intuitively. So shown here are a bunch of beakers of different colors. The thing that's blue is blue because it's absorbing red light. The thing that's yellow is yellow because it's absorbing something that's purple. And so that's a color wheel, sort of complementary color effect that you should just recognize. So in this color wheel, I kind of give you a sense of if something looks blue, it's absorbing the thing opposite from it, for example. You can read more about this effect, which is really visual perception, how light hits samples, by looking at this website. But the takeaway message is that when samples absorb light, they take away one of the frequencies of energy present in the entire spectrum that's hitting the sample. So for example, if you had white light, which is all colors, and you took away just one component of it, you would actually perceive a color to be present remaining. And that's really how we can conceptualize our perception of light absorption. As I said, we're kind of fortunate because we're going to actually measure absorption with the spectrometer and get around that color perception. What's going on when something's taking away light, when it's taking away a certain amount of energy that photons are providing to the sample? Well, the reason it's taking away that energy is because its atoms are starting off in the ground state. What that means is that those electrons that are bound coulombically to the nuclei of atoms actually exist in a state which is the ground state. It's the state when they don't have a lot of energy and they're just sort of sitting there. They're going to be in a ground state at room temperature, let's say. Now, if light comes along, it has some energy. So if we think about those electrons occupying like a ladder in terms of their energies, what they do is they absorb the appropriate energy and they go up the ladder. But because it's a ladder, if the energy is too big, then they would not be able to go in between two ladder levels and they don't absorb that light. If the energy is a little too small, well, they don't have enough energy to get up to the next rung. So they're going to only absorb light of very particular wavelengths that are matched to the energy levels that exist in the atom. So, for example, for hydrogen, its first transition, which is a 1s to 2p, and if you don't know what that means, that's okay. That transition is actually in the hard ultraviolet, or 122 nanometers. When that light's absorbed, the electrons go into what's called an excited state, and as I've shown here, now there's a black line, in fact, it would be off of this spectrum, and that black line represents the absence of 122 nanometers in the light that's going through the sample. So if you were doing white light spectroscopy, you would have like a black line in that region of the electromagnetic spectrum because your sample is absorbing it, but realize it wouldn't be absorbing light that's too high or too low in energy, only those particular energies that match the energy level spacings of the atoms. And in absorption, you're going from a ground state to an excited state, and you're taking away electromagnetic energy from whatever light is incident on the sample. Now, what that lets you do, and this is perhaps a different view of it, it means that electrons are getting promoted from the ground state to an excited state. And probably the most important thing to realize is that if you understand the atomic structure, you realize that different types of atoms are going to, first of all, have more than one electron, and they're going to have complicated kinds of energy levels, so you can get more than one absorption line from an atom. Now I want to talk about something different. I want to talk about emission, which is very much a related process, but distinctive. So here you see a neon light sign, and I grew up in Las Vegas, Nevada, so I'm very familiar with neon lights. And neon lights are an example where light is not getting absorbed, right? It's getting emitted. It's getting created by the sample. And that's going to be a different kind of process. It's going to have different ways of detection, different ways of excitation, and the spectrometers we use to detect it will be very different. There's a really good article on neon lights in Scientific American shown here if you want to read more about how they work. But in a neon light, what you're doing is you're putting a gas, and as you're going to see, it's really important in atomic spec to have a gas, not a liquid. and you're putting an electrical discharge. You're exciting the atoms with electricity, and you're making all those electrons very, very excited. They go up to these very high, typically empty energy levels, and they sit there. It's like they ran all the way up the ladder. They got so excited. But then, once that excitation goes away, or if it's in some sort of dynamic equilibrium, eventually they fall back down. And when they fall back down the ladder, they put out a photon. And that photon, or light, is what you're detecting. So light emission then is going to be the creation of light. It's not really the creation of light, it's the conversion of energy from an excitation source in the atoms to light that's emitted. And the color that's emitted, just like the absorbed color, will be a fingerprint of the atoms that were excited. So to use back to the ladder analogy, which I like very much, once I get over the fact that it's not an actual orbital, in emission, you're starting with atoms in an excited state. Now you got them excited through who knows what means. If it's a neon light, you zapped it with electricity. We're going to learn all about inductively coupled plasma, or ICP. And ICP excites them by putting atoms into a plasma. So that's another way to, so you can heat them up really, really high in temperature. And all of those things create emission of light. And that's happening because you're putting them up into an excited state and they're falling back down into the ground state. And it's kind of like you don't have enough energy to kind of always get them up into that excited state. So just as you're putting them back up, some are falling down, you're putting them back up, and some are falling down. And so that's what you're really doing when you're doing these experiments, is you're detecting the photons that come out. Now, what's really important about the photons that come out is you can see here the green light is getting absorbed, and that's going to be excitation that's not light. It's going to be thermal, it's going to be electrical, something to get atoms excited. Once they're excited, then they return to the ground state and they emit photons of very different energies. And a really important point is those different energies of the photons are a fingerprint for the atom. So for example, oxygen will have atomic emission lines right in this sort of blue range. These are the optical atomic emission lines. There could be others that are both lower energy or higher energy. Carbon, it turns out, has only really one that you're going to be able to detect, which actually makes carbon a difficult atom for a lot of atomic spectroscopy. It only has this one thing you can see. And then you can have chromium, or a lot of metals will have a lot. Now, why carbon only has one and oxygen has a lot has to do with something called selection rules, which is that you can't always go from one rung of the ladder to the other. Some rungs are not allowed. And again, that has to do with some very deep concepts of quantum mechanics and how orbitals are allowed to change shape or not allowed to change shape. But for our purposes, you don't really need to know much more than different atoms will have different kinds of light emission and absorption wavelengths, and those are the fingerprints of the atoms. So one of the cool things about atomic spectroscopy is you can have a whole party of atoms sitting in the gas phase that you're analyzing. You can have oxygen, chromium, uranium, silicon, but each of those is going to be emitting or absorbing its own characteristic fingerprint. And so you can actually do multi-element detection in some cases quite effectively. And that's going to be one of the things you're going to look at when you look at the different methods. Now, briefly, how do we see the light? Both absorption and emission involve the interaction of light with matter. And they're different, but at the end of the day, you got to detect photons. And you got to know what the energies are of the things you're detecting, because that's how you're going to deduce the concentration and the type of atom that was present in the sample. So you're going to do that with something called the spectrometer, which we'll talk a lot more about, but briefly, two components. One component, the monochrometer, is going to take the light coming from a sample and split it into its different wavelengths. For example, white light has energies of all across the visible spectrum, so we perceive it as white. But if you put it into a prism, you would separate it into the different colors. And all of you are probably familiar with that with rainbows or crystals. You see that kind of effect. Now, often in a spectrometer, you use something called a monochrometer, which has diffraction gratings, but it really serves the same purpose. It splits the light so that you can look at just one wavelength range in your analysis. So that's the first part, is splitting the light up into the different energies. Once you've done that, you're going to detect it. And like I said, you don't use your eye. You're probably going to use a solid state detector like a charge coupled device or a CCD, same thing that's in your iPhone camera. Or you might use a photomultiplier tube. That's kind of an old school technology, still around in some instruments. Much more complicated to run. CCDs are really replacing a lot of the photomultiplier tubes in many systems. So I want to do a little game with you if you want to pause right now. And I have the first question is I've given you 5 components. We've talked about absorption and emission. And I want you to arrange these so that they more or less would make an atomic absorption spectrometer. So go back and think about how you would arrange them and imagine from left to right the sequence of what would happen in the spectrometer, with the end goal being the detection of absorbed light by atoms. Okay, I don't know how you did, but here's what I did. So in absorption, what you first need is a light source. Because in absorption, you're going to put the sample between the light source and a spectrometer and detector. And from that, you're going to try to figure out what light was absorbed. So you need a light source, the sample, spectrometer or monochrometer, or detector. Now sometimes a detector can be part of the spectrometer, sometimes not. It just depends. So the most important thing is you have a light source, and it's also very much in this geometry. The light source has to pass through the sample, and you have to sit at the end and detect it. So let's try atomic emission. How would this look different? Now, to do emission, you can see the answer here. It looks a little bit different than absorption. And the real difference is that in emission, you have to start with atoms in the excited state. So you got to excite them somehow. And so the excitation source has to be present. Often that's not in line with the monochrometer. Sometimes it matters, sometimes it doesn't. I've also in this slide tried to clean up the terminology monochrometer, detector, and spectrometer. A spectrometer usually consists of all the stuff you have to do to figure out what wavelengths of light and how much of the light you have at each wavelength. That's kind of a limited definition, but probably appropriate for what we'll be doing. And so the monochrometer and the detector together would form a spectrometer. So as you can see, in both atomic absorption and emission, you needed a spectrometer, but the front end of the system was very different. In one case, we needed a light source, and the other case, we had to excite the atoms. So I hope you've gotten a sense of the basics of atomic spectroscopy. We'll be moving now more into the instrumental world about how these things are put together and some of their advantages and disadvantages. Thanks so much, and see you next time.